So today we're going to discuss part 2 of module 2 for the subject bridge engineering. So last meeting we were able to discuss the different design philosophies or design of safety that we apply in bridge design. And as we have discussed, almost all of this design's philosophy, especially the load resistance factor design, will be based on the limit states. When we say limit states, this would now be the ASHTO code that is intended to provide buildable and serviceable bridge that is capable of safely carrying design loads or specifying lifespan. So when we see lifespan of a bridge, that is given to be 75 years. So when we are designing bridges, we should expect that our design should be able to be serviceable within 75 years. So a limit state is defined by AISC-LRFD as a condition which would represent the limit of structural usefulness. It means this is a boundary between the desired and undesired performance of the structure. It's a condition beyond which the bridge or the component of the bridge would cease to satisfy the provisions for which it was designed. So from the term itself, the limit state, it's the limit, okay, so at which the bridge will be able to be of service, of use to the purpose it was designed. So for our limit states, we have 4 different limit states. That is the strength limit state, the service limit state, the fatigue and fracture limit state, and the extreme event limit state. The strength limit state is a limit state that would ensure that both local and global strength and stability of a structure is capable to resist statistically significant load combinations experienced during the design life of a bridge. While for service limit state, this is now used to control the stress, the deformation, deflection, and crack width under normal service conditions to ensure structure serviceability. For fatigue and fracture limit state, this would now apply to restrictions on the stress range under regular service conditions, reflecting the number of expected stress range excursions. When we say extreme event limit state, this would now cover structural survival of the bridge component or a system during rare events. And when we say extreme events, this would now include phenomena such as your earthquake, or in the Philippines, we have the typhoon. In the US, we have the hurricanes. So for our limit states, for the strength limit state, it defines now the safe operation and the adequacy of structure under normal or extreme load condition. So for strength limit state, it would both be designed for the usual phenomenons or usual conditions under our design, and for strength limit state, we would also use this to design extreme load conditions. So the strength of structure based on its limits would be defined by the yield strength and the ultimate strength, the buckling and overturning of the bridge. For the serviceability or the service limit states, the serviceability will be defined as the performance and behavior of the structure under nominal service condition. So the serviceability would be defined by the stress, the fatigue, and the deflection, and the vibration and crack width of that is present during the design life of the bridge. For the AASHTO LRFD specifications, each member and connections or components of the bridge should satisfy the following. For strength 1 of the strength limit state, it should follow that the basic load combination would relate to normal vehicular use of structure without wind or any extreme event loads, such as earthquake. And strength 1 is mostly applied to control the superstructure member. For strength 2, this is used for owner-specified special design vehicles or permit vehicles. There's no wind or extreme event loads considered under strength 2. And though this is existing, it is not commonly used, as we always usually design our bridges, highway bridges, using HL93 loading, and there is usually no owner specified or yung customized design ng bridge. So for strength 2, this will now reduce the dynamic load allowance in our designs based on the special design of our loading. And then we have strength 3, which is used on bridges that is exposed to maximum wind velocity. And we are expecting no live loads as assumed that is present on the bridge. Okay? So for strength 3, why do we expect that there is no wind during this or no vehicle load during this scenario? So basically, if there are strong winds, such as hurricanes or very strong typhoons, let's say signal number 4, signal number 5, usually we avoid placing vehicles on the bridge to avoid accidents. Likewise, we the use of the vehicle or of the bridge by vehicles would be avoided. So next we have strength 4, which is used for structures with very high dead live load force effect ratio. So if we have very big structures, very heavy structures, this would be the strength limit that we are going to use in our design. So this control load combinations for certain elements or components of the bridge if the structure would have long span length or large dead loads and the bridges are under construction. So under strength 4, we have to make sure that various type of bridges would have similar failure probability. For strength 5, this would now relate to normal vehicular use of the bridge with wind velocity of 55 miles per hour, or that's 90 kilometers per hour. So live and wind load will be combined in this design. Both values will be reduced because of probability that there is a very low experience of heavy live load and extreme high wind load. So it's the same as what I have explained with strength number 3. So if there's high wind load, we avoid the existence or the usage of the bridge by the vehicle or the live load. So next we have the service 1, which is used for normal operational use within 55 miles per hour wind. all loads will be taken at nominal values, and extreme loads are excluded. So extreme loads, earthquake, or wind load moving greater than the 55 miles per hour. So service 1 will be used to control the deflection, the crack width for reinforced concrete, and the compressive stress for pre-stressed concrete, and the soil slope stability of our bridge site. Then we have service 2, which would prevent the yielding steel due to the vehicle live load. The live load use is approximately halfway between service 1 and strength 1. Then we have service 3, which would relate only to tension in pre-stressed concrete superstructure. So service 3 would be used only for bridges that would be made up of pre-stressed concrete. So the load factor of 0.8 will be applied to the live loads. That is, if nominal design live load is used, the superstructure will be over-designed for concrete tensile areas. Therefore, you have to use the load factor so as not to have an over-design. Next, we have service 4, which would relate only to tension in pre-stressed concrete substructure to control the crack. So the load factor for the wind now will be applied, which is equal to 0.70. And we are assuming that under service 4, the wind load will now be moving at 84 miles per hour. So this would now reflect probability of our substructure will be subjected to tensile stress once every 11 years. Next, we have your fatigue limit state. Under fatigue limit state, this is now a combination of both fatigue and fracture load combinations. So this would relate to repetitive gravitational vehicular live load and dynamic responses. So as we know that fatigue would be present as the bridge is constantly used. So live load factor will be applied, and that would be 0.75, would represent now the cumulative effects of the majority truck population. So there's only a single 32 keep load at 30 feet constant pacing that will be applied in our design using fatigue limits. Under extreme event, we have extreme event 1, which would be related to earthquake load. So live load considered shall be based on daily traffic volume of bridges. So unlike the wind load, so wind load we do not, or we assume that there are no live loads, no vehicle loads on the bridge. And then for earthquake, there will still be live loads because earthquake happening would be unpredictable. So there is possibility that there are live loads on the bridge while an earthquake will occur. Therefore, under extreme event, we will have both earthquake load and live load present in the design. So for a normal bridge, the live load factor under extreme event would be 0.5, which will imply low probability maximum live load at the time of large earthquake. And then we have extreme event 2, which will be used for extreme conditions. Examples of these extreme conditions will be your ice load. So if we are designing bridges for areas that have winter, so ice load, nagbuo or naipon yung snow. So that's this one. Other extreme conditions would include vehicle collisions or vessel collisions on the bridge. So this only, or this event only should be considered, or one of these events should only be considered one at a time during your design. So in the design, you only design if you're expecting ice load, but you should not expect that both ice load or collision will occur under extreme event. So under extreme event 2, you will reduce the live loads considered in your design. So live loads will be reduced since pag merong ice load, usually hindi masyadong ginagamit yung highway bridge, and when there's collision of vehicles, there would now be reduction of traffic because of the vehicles that is constricting traffic flow.